Welcome to Chemistry at Hononegah High School. I'm Brian Round, and today we're going to be looking at our fourth set of notes from our mole chapter. Today we're going to talk about what's known as percent composition, which is exactly what it sounds like. Composition means what it's made up of, and what we're going to be looking at is the percent of each element that's present in a composition and how to calculate and how to use it. Now we're talking about percents, so before we get into percent composition and chemistry percents, let's look at the concept of percent as just a background information and ways in which you've already done it. So how would you calculate the percent of females in the room? Well, you'd count the number of females, you'd count the number of people, you'd take females divided by people, you'd multiply by 100, and you'd calculate the percent female. Now, all percents are essentially the same. So if we're looking at percent males, percent females, percent anything, it's all fundamentally the same math idea. The part that we're studying divided by the whole thing, that gets us as a per 1 ratio. And to get it to a per 100 ratio, we just multiply by 100. So part over whole times 100 is what all percents are. So if we're doing percent composition, mathematically we have to be doing the exact same thing. The part that we're studying, that's got to go on top. What the whole thing would be, that's got to go on the bottom. And then we divide to get it to a per 100 ratio, we have to multiply it by 1. So percent composition is the percent by mass of each element in a compound. So you look at the mass of the element that's present, divide it by the mass of the whole compound, multiply by 100, and you have your percent composition. Now, remember the mass of the compound is what we've been talking about as molar mass. So in these particular cases, what we're actually doing is looking at the mass of 1 mole and of the element. So if we had 1 mole of the compound, what mass is this element, what mass is that element, and what would be the mass of the whole thing? That's really the part in the whole that we're actually studying, is molar mass parts for all intents and purposes. So what we're going to do is look at the percent composition of each of the elements in water. Now, we know we've got in water hydrogen and oxygen, and based upon the formula for water, H2O, we know we have 2 hydrogens and 1 oxygen. Now the 2 hydrogens, if I had 1 mole of water, that would mean 2 moles of hydrogen atoms. That's 2 times 1.0, 2.0 grams. 1 mole of water would have 16.0 grams of oxygen in it. So what this has established is how much hydrogen I've got and how much oxygen. The only thing I really don't know is my whole. Well, and you find that just by adding the two together. So 18.0 would be the mass of the whole thing. So if we have an element, the easiest way to, or I should say, if we have a compound, pretend we have 1 mole of the compound and we can figure out all the masses. Now, if we are actually given the mass of the hydrogen, the mass of the oxygen, and the mass of the whole thing, we can just plug into the original equation. We don't have to do any molar mass calculations, simply because they're telling us the mass of the element, put it on top. They're telling us the mass of the compound, put it on the bottom. Divide and multiply by 100, we get the same thing. But if all we have is the formula, we've got to use our periodic table and molar masses off the periodic table to figure this out. So the percent hydrogen would be the mass of the hydrogen. Well, in our sample size, we said we had 2 grams, and our whole sample size was 18.0. So 2.0 over 18.0 times 100, that's going to give us to 2 sig figs, 11% hydrogen. Now, you might be thinking, well, wait a second. If this is the amount of hydrogen, and the only thing left is oxygen, and I know the total percent should add up to 100, you might want to quickly do 100 minus 11% to get your answer. The problem is you have to take a look at the numbers we're using in the appropriate sig figs, because we're going to end up sometimes with slight rounding differences. We might not exactly equal 100. We might equal 99.9, 100.1. We're going to be very, very, very close to 100 though. And if you've made a mistake in the first one and you simply subtract it from 100, you now have both wrong. You're much better off calculating them independently and then using the 100% as a double check. So mass of oxygen, 16.0, mass of water, 18.0, 16.0 over 18.0 times 100. Now I've got everything with 3 sig figs. 16.0 and 18.0 have 3 sig figs. 100 is an exact number, so that's unlimited. Now I get to round this one to 3 sig figs, and I end up with 88.9. Now 11 plus 88.9, that equals 99.9. That's essentially 100% to within rounding. So that's a good double check that I did it right. So any compound formula that you're given, you could break it apart in this way and calculate the percent compositions of each of the elements in there. Now, sometimes books don't get into this concept, but there is something I do want you to understand as an implication of these numbers, because these aren't just numbers we're making up. These are real numbers based upon the formula, and they have applications. So what would be an example of an application here? Well, let's say we had a glass of water that contained 648 grams of water. Now, is there any way I could use my percent compositions to actually figure out how much hydrogen it would actually have in it? Well, yeah, there is. I just determined 11% of any sample of water is going to be hydrogen. So all I really need to do is take 11% of 648. Well, remember, we artificially multiply by 100, so we have to divide by 100 to get it back to a decimal. And then we multiply it by our 648, and we would calculate how much water. Now, paying attention to six figs, 648 grams had 3, 11% only had 2. My best answer here would be to say I have around 71 grams of hydrogen. But it would be a quick, easy way for me to determine how much hydrogen was in that sample. So if I know it's water and I can calculate water's percent hydrogen, I can take that percent of any sample size of water and actually figure out how much hydrogen I've got. And the same token, I could use my percent composition of my oxygen in water and convert that back to a decimal, multiply it by my 648, and I could calculate how much oxygen was in there as well. So remember, if we can calculate a percent, we can use a percent as well. And sometimes that's overlooked by students and textbooks. Now, other thing that I want to talk related to this is, let's say we're looking at a more complex type of molecule. If you've ever gotten a pharmaceutical from your doctor and you open up the container, there's always this little piece of paper that folds out to be super long. And somewhere on there, besides all the really other tiny things that talk about drug interactions and all kinds of other things that it mentioned, somewhere in there it will show you a picture of it. So if we look at this particular substance, and this is caffeine, something we should all be familiar with, I'm missing a bunch of stuff. So if I've got a picture like this, what have they done to actually hide some of the atoms? Well, they did it to try and, excuse me, make the picture a little bit easier. And what you need to understand is these lines are bonds. Remember, we drew molecules in first semester, and obviously one line would be one bond, two lines would be a double bond. But those lines have to connect to something. So we're missing some things at where those things connect. And what we're actually missing is our carbons. So we see some carbons that they've shown us, but we have carbons at every one of these positions as well. So we've got carbon in each one of those spots. And if we were trying to count these things up to figure out how many carbons to calculate the percent carbon, I need to recognize in that picture that they just didn't bother to write the carbons. Now, the next thing you need to realize here is there's another missing thing. We're missing some hydrogens. I know you see some, but there's also some hydrogens that we're missing. Now, remember, carbon, like all substances that have a full octet, needed a total of 8 shared electrons. Well, if you look at this carbon right here, it's only got 3 bonds coming off of it right now. That's only 6 electrons. And carbons never had unshared pairs. That's because there's another thing they neglected to show here that is very, very common. Besides the fact that they deleted the carbon that's in this position right here, the other thing they do, and they realize that if you really know chemistry, you could figure it out, is at this position we actually had a hydrogen. So anywhere where you see 3 lines, we actually have a hydrogen there as well. So in the case, and that's to a carbon. So in the case of this carbon right here, it's got 4 bonds, it's okay. This carbon, 4 bonds, it's okay. This carbon, 4 bonds, it's okay. This carbon, 4 bonds, it's okay. We've now found all of our hidden substances. So now I can actually count what it is. So I see I've got 4 nitrogens. I see I've got 2 oxygens. Those stand out. The tricky ones are the carbons and hydrogens because some of them are hidden in this type of structural formula. So it just makes it too complex to stick in those carbons and those hydrogens. So a chemist would have to look at this to really figure out what's there. So in this case, I know I've got a total of 8 carbons if I count my 5 missing ones that weren't written. And then as far as my hydrogens, well, I see 3, 6, 9 around the outside, but then I have that one hidden one over in that other position. And now I've got the correct formula. Now I could go on to calculate the percent composition. So I would find out what 8 carbons weigh, what 10 hydrogens weigh, what 4 nitrogens weigh, what 2 oxygens weigh, add up the total, and I've got my parts and my wholes. I could calculate what the percent composition is. So in your homework, I'm going to have you do one of these. So remember, that's how you count this type of picture. And that ends our set of notes. Good luck.